Так. Добрый день. Hello.
Hello.
Who is here?
Everyone is
Hear
here.
me?
Может заглянуть. Андрей Михайлович, все здесь, но видите вы только нас.
Сейчас я никого не вижу, кроме себя в маленьком окошке в правом углу экрана.
Андрей
Еще?
Михайлович,
А вот теперь вас вижу.
но вас сейчас все видят.
Но это прекрасно. А слышат?
Да.
Да.
То есть начинать.
Yeah.
Okay, friends. It's very nice. It's great that it's possible to say a few words in the beginning of this conference to all of you. Unfortunately, I don't see you. I would have said to you that it's great pleasure to see so many people here in the audience, but unfortunately, I don't know how many people is here. I don't see you, but I'm sure there is a lot of people, and it's a great event for MIPT, the school. For me, it's a great pleasure to understand that MIPT, Moscow Institute of Physics and Technology, is now one of the best places in the world, I would say, in the field of artificial intelligence. And of course, it's a great attraction for students and for many professors who are coming here at MIPT to work on artificial intelligence, to listen for lectures on artificial intelligence. And MIPT has got a Center of Artificial Intelligence more than 1 year ago, and this is a great achievement of our university, of our institute. So it's my great pleasure once again to welcome all of you at this conference in the walls of MIPT, and I wish you a very fruitful event, a lot of interesting lectures, hackathons, seminars, meetings, and possible interesting discussions, I don't know, everything, many fruitful histories, many fruitful stories afterwards and so on. I hope a lot of people will come here again many times, and maybe some of you will become our students or our teachers, our professors. So welcome, and have a very nice meeting during these 5 days of the conference of the school. Thank you.
Thank you. Say goodbye.
Спасибо всем, по-русски.
Yeah. And move along. After this great introductory video from Andrei Prigorodsky, director of FizTech School, we move forward, and before our first lecture, just a few organizational words. Today, all our activities are held here, so we didn't move to other building. All lectures on this floor and this lecture hall, and coffee breaks, poster session, and opening dinner maybe. It's on the second floor. And one quick note, opening dinner is combined with poster session. It's not after poster session, it's at the same time, on the same floor, same place. So, once again, welcome to our school, and we move to our first speaker, Michal Valko, from India from DeepMind, and his lecture Active Multiple Matrix Completion with Adaptive Multiple Sets. It's your stage now.
Thank you very much. I would like to first thank organizer for inviting me. I'm also lucky that I can see you, unlike the guy before me. So it's great. So I work in France or in multiple areas. I am mostly focused on online learning. When I was deciding what I'm going to speak about, I selected one particular talk, but I'm happy to chat later about other aspects of online learning in particular and AI. if I can be useful for what they were trying to do in your own research. So right, I work in DeepMind Paris, which is a company trying to solve a general AI. I also am affiliated with a public institute of applied mathematics called INRIA in France, and also give lectures in École Normale Supérieure for a master in machine learning. It's for the last 20 years. So, but let's get to the meat. I didn't take my watches, so I should have 1 hour or 45 minutes plus questions, right? Is it correct? Okay. So I'll try to time myself and not to take much time. All right. So let's talk about something that we all understand, and so how the people used to make money for a long time. This is market segmentation, right? We all know that the way how we can deliver some products that we do is like, we learn about which of our sub-markets prefer, and then we deliver product to them, right? So in some market could be, we can look at the people from, different areas, right? Like, for example, different gender, different age groups, and so on, right? Like the most common success story in economics is, it's coupons, right? You give coupons for people to go to the grocery store and buy actually the same product for lower price, and that's why everybody gets the product for their price, and that's you earn more money. That's one of the things that economics work, and market segmentation is a huge and important part of a lot of product selling. And so in this talk, we try to see how we can optimize this and actually learn about what market likes faster, right? This is, I make this economic, capitalistic, motivation, but this is in general to see how can we learn about different subgroups more efficiently than with traditional methods, with some kind of machine learning online perspective, right? So I'll just kind of assume that whole population is composed with different markets, and I try to learn what they like as fast as possible, right? And so, and then once I learn what they are, I can deliver better product from them. But most importantly, if all markets were same, that will be a simple task. I have my marketing budget. I will split my budget into different populations, and I send the people there, ask their questions. However, these sub-markets are different. Whenever I subsample, divide markets into population, they have different size. So, maybe I care about some markets in a different way because they're a bigger market. They have different complexity. There are some people in some areas, the people all like the same stuff. Let's say, there are, some very complicated people here in Moscow, right? They have a lot of very different preferences, but maybe in the more rural areas, they have they more care for one product. I mean, that's an example. The thing is that, if we have infinite amount of budget, and budget could be not necessarily money, it could be amount of time I can spend on talking to people, oftentimes when we do market tests, we send people to streets and give them questions, or we give some products for free. I live next to the market agency like that. There are people outside the question. They know me because they serve, and I go there every day. And so they often try to get me some product to test, right? So what was it like last week? Last week they gave me like 2 pizzas, and they said, well, first you eat one today and one in next 2 weeks, and then you rate them. And based on that, of course they ask my age, my preferences to deliver such things, right? So there are companies doing that, and so this costs a lot of resources. And my talk is about how to optimize these resources effectively, because our budget is always tight, right? Nobody tells you have infinite amount of time or money. And reasonable things happen, right? So we have a small market. We need lower budget to discover what it is, and also smaller complexity, smaller diversity. It's also lower budget, right? So we should not spend as much time as possible to do it. All right. So the thing is that we know the size. Once we separate some markets in some kind of subdivision, we know the size of the population. Some it could be geographical. These are national statistics. It's easy to know what is. But what we don't know is actually the complexity, right? So what we're trying to do here in this talk is to see that how to adapt to this structure complexity of the market, right? So, and I'll discuss when it is possible and when it is not. And once we know it, we can learn how to do it faster. So this is one of the examples of the areas of active learning. So you don't no longer, you try to see, well, let's just design how things work and let it go. Like, how many of you know A/B testing? Can I give a show of hands? Have you heard of it? Okay, about half of them, right? So, so the A/B testing is just very, normal, traditional marketing procedures. Like, for example, I have, I don't know, 2 websites, and I design one way, one another way. I get 50% of people go to one, 50% to the other, and then I decide which one is the best. The thing is that this may be not the best possible, because in advance, I decided to spend 50% of budget on one and 50 on the other. But if I knew that, okay, well, already after few iterations of one, people dislike it, I should stop and use my budget more efficiently, right? So A/B testing kind of offline, passive way, because in the beginning I design this experiment and I wait, and I need to wait until the final and get the result. Here I try to adapt. So every time step, I decide what to do next and adapt, so I can be more efficient, right? So the setting could be if every time step, in our particular example, I zoom on one particular sub-market, and the nature gives me answer, right? Nature gives nature. Like, for example, I send person to ask them question, what do you like? And I give the example. I get the answer. Well, and then I can zoom another sub-market. I can send a person, or I can pick up the call and call the person for sub-market. And based on their answer, I can adapt and decide which sub-market I should learn next. So, and nature gives us one sample. That means, like, I ask, do you like this kind of music? What kind of butter you prefer? Do you like a salty or creamy or something like that? All right, and this I repeat. I keep repeating until I just get my final answer, or until I exhausted my budget. And the hope is that with this kind of setup, I'm able to do better than the passive setup this way. All right, so I should disable this somehow. Huh? Yeah, it should be quick. Yes, this is my break, so I don't spend too much time on the computer. So this is my app that tells me, like, every few seconds, don't touch the computer. But I think I will disable a bit, because this will come again soon. Because if you keep ignoring it, it gets more aggressive. So it's very adaptive too, right? All right, so I will speak now about one particular problem to talk about something specific. But please ask me any question even now if you have, and please interrupt me as much as possible. I don't want to go through all the slides. I want to be most useful for what you. So is this general setup clear? Do you have specific question or general question about how this works and why it makes sense to do that? All right. So please ask me as many questions possible during the talk. So let's go to specifics. So let's say I have several regions that I want to sell my product, right? I have a city here, and I'll particularly, decide what the market is and what it's learning. It's maybe very vague. So let's talk about, like, I'm trying to complete the matrix, right? So here we have all the people living in the Moscow, and here there are all the products that I could have, right? I cannot ask about all the products I'm trying to sell to all the people, right? There are like 20 million here. That's too much, right? I can ask a few questions, so I can have, very sparse answer. This person likes this person likes this, and so on. I'll be more specific on the next slide. But what I would like to know, if I'm a company, I would like to somehow complete, learn about everything. So with few questions, find what everybody likes. And then I can do better decisions. And for example, one way, and it's not the way, but one way, we can just say, well, it's just a matrix completion problem. We define this precisely a little bit later. And there's some special rank, right? So the rank of the matrix. Who knows what's the rank of the matrix? I think everybody should know. Okay, fine. I'll go faster. So we try to complete basically, and the rank of the matrix just kind of a number of degrees of freedom. And if the rank is low, we just need a smaller number of entries to complete it well because we have lower number of string, right? And this is some other, the oblast of Russia, right? So I said, we have different sizes. For example, this is a bigger, big size population, but maybe, people are, very, uniform and they have smaller rank. The matrix is small, but I don't know this. If I knew that here people have this kind of rank, so I need kind of like 100 degrees of freedom of describe all the population in Moscow, and I could devise my budget appropriately. The things I know the size, how many people live in all these regions, but I don't know what the rank are, because that could be also specific. Maybe for some other products, this matrix would have rank 2 million, and this would have rank 1. So it's very specific, and so I would like to adapt to it. So in reality, I never know the rank, but I would like to act optimally as if I knew the rank in advance, right? So here I specify, I said a complexity rank, but a lot of things that I'll see in these talks will apply to any kind of complexity. All right. So whatever I have. Now the setup is every time step I can send or call person one of these regions, and I get an answer for it. I get the one particular, sample from the matrix. So I make them as matrix node that I believe this region has or this shape, right? So these are now matrices. So at the time step, we get a sample from the region that we chose, right? So what does it mean to get a sample? So there are particular models that model, how the sample arrive. We describe few of them and see what is possible. So one of the models is called Bernoulli model. So in that case, what you have every time step, you flip a coin for each of the entries, and you decide if you get a sample. So every time step, I can with probability whatever 0.3, I get this one. So I flip a coin and I get the person, the Adam, for how much he likes this Marvel movie, right? And he said I don't like it, and the next one we'll just come up with random. And we can even consider uniformly at random, right? So I flip a coin and I get samples from one of them. For simplicity, I can just assume that matrices are squared, because otherwise I would have D1, D2. So I will say that D is the size of the matrix. And then I get some noisy version of the output, right? So it's not true that I always get the right answer, because somebody went to the movie, and because there was a lot of noise, he doesn't like the movie. So I don't often get precise information, but I can get I get the noisy information. So here that's why I decided wherever I get a sample. So 0, 1, do I see or not? Here it's the real value of the sample. I would like to know this for everybody, but I only would know it for when this ends up being 1. And I don't have the real value, I have a noise value. Right? Is this clear? Okay. So the specificity of this model, I didn't create this model. So this model was studied in Kolchinsky and Chibako in 2011. How the matrix arrives and how I could complete the matrix is that each of the entry is observed either 0 once. I never get to see multiple views of the same entry. That's because this is how it works. Every entry has some kind of hidden probability. Let's say 1 over d squared. I flip the d squared coins. I see how many end up 1, and for that I have an answer. All right. So there is another model called trace regression model, almost the same, with one difference, is that now I don't flip a coin for each of them. I say every time I decide which entry you want to be rerolled. So I sample uniformly at random one of the d entries, almost the same as before, and I get this entry plus the noise. So this is how it works like. So in this model, it's almost the same. On expectation, we have same number of entries revealed. But what happens here, I can receive answer for the same entry twice or 3 times or 4 times, right? It's like if I went to the movie several times, and I would evaluate the movie. Or if I listen to some song several times, and I would evaluate the movie, right? So it could have, if I'm a consistent person, right, I will get the same answer. If I'm not consistent, I can say, okay, first time I like it, second time I didn't like it. So the main difference between this is that each of the entry is observed, 0 or multiple times. So I can have this multiple observation model. And we will consider specific realistic situation, we call it also high dimensional situation, where number of possible entries is much bigger than the sample budget, right? This is the most realistic way, because in the other case, when this is the reverse, it means like I have more budget than asking all people in Moscow what movies they like for each of the movies, right? I will never have money for or resource or time for doing that, right? So, and also there are also much simple ways. If I have that much budget, I can just ask for every question several times, do the averages, and this is simplest thing to do, and this is minimax optimal, and I cannot do better. Here I care about situations more realistic that I only observe very few entries, because I have my boss gave me money for a few hundred of calls, because they all calls. So is this clear? Any questions about these models? Any question whatsoever? All right. So let's go about this phase regression model, because we will spend most of the time on this one. When does it make sense to consider it? Because maybe it's not very common that we go to see same movie several times, right? So maybe that is not appropriate. So in which case this is more appropriate. So naturally it's like music recommendation. So in India we worked with a company called Deezer. I don't know if you know it. So it's a kind of music recommendation website that tells you what music you should listen. That's quite normal to listen to music several times, right? There people become fanatic and just like keep one song in the loop, and we see that, right? And so that way you have multiple observation of the same song. You can also say, well, people don't narrate songs all the time because they just prefer to, listen to them in the metro. But for us, when we work with them, for us, the feedback is also not skipping. If you don't skip the song, it means kind of that you like it. It's a soft feedback. The nice thing to do, this multi-sampling, so listening same song twice or 3 times, it really occurs there. So celebrating or skips. And now there's a tasting experiment. My example with pizza, exactly, I give you one pizza today, one pizza 2 weeks later, and these are maybe the same pizzas, and I ask you for opinion to have some variance if you're consistent opinion, so I don't make wrong choices. I have more statistical power to say something. So asking for opinion second time. So like these 2 examples are kind of different in a way that here it's like happen naturally, that sometimes I just ask for opinion several times, and here I do it by design. I want this to happen because I want this model to be realized, so I make it so because I know some properties. So because I'm the advertiser, I'm deciding who gets asked a question next. All right, so we can also, just sometimes it doesn't make sense that, okay, well, I watched one movie several times, for example, on Netflix, but we can even, not learn about one specific movie, but one specific series. And then sampling, meaning just watching one episode. So even where it's not possible or not natural that I ask same question to the same person, I can, same question meaning, for example, watching different episodes from the same series. All right. So now we try to see how to actually solve this just for one matrix first, because before we try to optimize over multiple matrices. So the methods for matrix completions, they're countless. This is one that won the matrix challenge, the Netflix matrix challenge for I think $1 million. So there seems a lot of methods that have some different guarantees and different properties. So the one that's the most common use is alternating list square minimization. You can do gradient descent. You can do soft impute. This is something that all available, right? The methods that just you give it some entries of the matrix and ask me complete me the rest of the matrix. Assuming that the matrix has low rank. Sometimes I need to give it the rank. So this problem is called estimation, right? So I I have some matrix M0. I don't know this. This is the real taste of people that I will never discover. And after n samples, n questions, I get my estimator. And then, I'd like to see that that the difference in a Frobenius norm, it's some function of a rank, of the size and number of samples, obviously, right? And I would like it to be, decreasing with n or with other things as, it'll be as small as possible, right? So, particularly, I remind we still consider this high regime that, we have at least these samples, but smaller than d squared. All right. The thing is that, like, good estimator should be adaptive to the rank without knowing it, right? Because it's much easy to say, well, look for the best matrix in the all 100 rank, all matrices with the rank 100. But, realistically, we never know it. So ideally, we would like to say, well, the lower the rank is, the smaller the error will be, right? This is natural, right? You have also holds for other stuff. The bigger the n is, the smaller the it is, right? So if you had such a good estimator, with lower rank, should be just better, right? This number should be smaller. So for example, there is an estimator called square root lasso estimator. It's very simple. It's almost like linear regression. So you just look at the samples that you have, and you try to minimum among all possible matrices. See, I don't know the rank. I try to minimize, so I look at all the matrices, and I try to see which one has a minimal square root, which one has a minimal error on these matrices, regularized by nuclear norm, some of the eigenvalues for the matrix. Right. So here, of course, so since this is growing in the rank, so the lower rank matrices are preferred. But I don't need to know which one is. So it's kind of a trade-off between the fit and the low rankedness of the matrix. All right. So what can we know for this estimator? So this estimator is adaptive. So Olga Klopp, actually coincidentally I had lunch with her 2 days ago, she proved that for this matrix, for this square lasso estimator, so defining the matrix n hats because of this estimator, it scales as a constant sum, rank times d, so dimension of matrix divided by number of samples, right? So the smaller the rank is, the smaller the error will be, right? So this is the error that we have. And so the smaller rank, the smaller the error will be. And I never needed to tell, you don't see any R here, what is the rank of the matrix, right? And the thing is that you cannot do much better because Kolchinsky, Lucchini, and Chibakov, they proved later, or actually earlier, that you need at least R times these samples. I'm not talking about these constants; they're not important, right? So the only difference between this is just log d term, which is a small number, right? We have a number. So there's the only log gap between the upper bound and lower bound. So this is almost minimax optimal. So this estimator, or the other one, you cannot do much better. This is the best you can hope for single matrix completion with unknown rank. So other thing is we would like to this estimator also to be adaptive, right? So what does it mean to have adaptive estimation? So the thing is that not only would like to have so in the traditional statistics, when we look, for example, for simple statistics as average, we also say how we would like the method to answer, well, how confident you are that the average that you're giving me is close to the true mean of the distribution, right? So in how the statistician answer to that, you give you like a confidence interval, right? Okay, for example, in simple Gaussians, you have, okay, this is what I believe my the mean is, but I have some kind of deviation, 2 sigma plus or minus. So this is my confidence that I believe that my true value is instead of that. So we would like to have a similar case for matrices, right? Matrices are not numbers, so we will not have intervals of matrices, but what you can have is a confidence regions. So we can just say, well, this is a set of the matrices, which one of them is a true one, and this set is small. So the smaller the set, the more confident we are that the true estimate is the real one. And also we would like to know that that this error is also smaller when the complexity of the matrix, where the rank of the matrix is smaller. So again, we would like to have also these adaptive estimators. So, and what this particular mean? That is that, you know, if we have, for example, two different ranks that we have, that we actually get the rate of the smaller one. So I repeat again, not to lose you. So let's go back into this adaptive estimation, right? So let's see. We have just two possibilities. You know, the matrix could have rank 5 or rank 100. And so the thing is that we would like to know if the matrix has rank 5, we would like to get the error of matrices of rank 5. And if the matrix has error 100, we would like to have a matrix of error 100. But we would not want to tell them, and we would not want to have a slower rate. So the rate, how it's be defined, is that, you know, so we want the expectation of the all possible completion of the matrix is some function of the rank, right? So the C times the rank of the smaller class that we have. And so Keshelans proved in 2009 that actually these estimators of the Fs exist for both models. So remember, I told you about, you know, the trace regression model and the Bernoulli model, right? So I have different ways how the matrices could arrive, you know, depending on the rate. And we know that this estimator exists for both of the models. So, you know, in that case, both of the models are equivalent. And now let's talk about these confidence sets. Because learning is not only the estimation, but it's also confidence estimation, right? And so the result, much recent, just a few years ago, is that these confidence sets sometimes exist and sometimes they don't. And actually, this depends on which of the model, which are almost similar. So let's be more specific. So, for example, for this trace regression model, when we have these double entries, so I can listen to the same music twice, we can construct alpha confidence region. Why I call them alpha? Because I want that with probability 1 minus alpha, the true matrix is in this region, right? So I can create you a set of the matrices, and I can claim that the true matrix lies there with probability 1 minus alpha, and the region will be as small as the true rank of the matrix. So, sorry, to be specific, if the rank is smaller, this region will be smaller. In Bernoulli model, we can actually prove that it can never exist. So in the stamp, when we have this, when we don't have double entries, we cannot have such a thing. It's impossible. And so this distinction was kind of will be important if we can actually adapt to these markets for our primary goal. So already, and this is very fine because, for example, if I already tell you the noise variance, they start to exist again. So, you know, there is very fine boundary between the models. What do you need to know and what you don't need to know when there's very sharp distinction whether it's absolutely impossible something exists and you can prove it. And we will do that. So in our trace regression model, this adaptive estimation is possible, but adaptive confidence sets is often impossible. And so I'm talking about matrices, you know, today. But this is true for a lot of things: estimation of function smoothness, estimation of some kind of general classes of Holder operators. And this is very common case in statistics that you can construct the adaptive estimators. So, for example, this square root estimator for matrices, but the confidence is often impossible. And so, when it is possible, this is one example here: double sample music recommendation. Then we are in big luck because we can use our budget actively and efficiently. And this will be in the second half of the talk. Okay, so I'm right on the time. So what is important? Why sometimes possible? You know, I didn't say why it's possible. I'm just claiming those things, right? The important thing is that once we have double samples in the cells of the matrix, we have this noise variance. So we can already, when we have two, we can say something about the variance. Well, you cannot construct the variance estimated from one sample. That will be silly. But we already can construct it from the two. So we can adaptively bound the error of the estimate. We'll show you exactly what it means and how. All right? So I'll skip ahead just to announce what that means. So we will be able to construct, so this is the true estimate, this is the error, this part is the error, and this is the estimator of the error itself, right? So first we have an estimate, the matrix. This is a true matrix, we never know. So this is the error, but since we don't know the matrix, we cannot know the error. It will be nice to know how the error is. But what I'm constructing is estimator of the error. So I don't know this, but I will know this, and I will show you that this could be small. So here I can not only construct the estimator, but I can construct the error of this estimator. Again, in a simple average, this is trivial, but in matrices, it's not. And so the beauty of this that you don't see right here, right now, that this can be upper bounded by something depending on number of samples and the dimensions, but the estimator plus the confidence interval of the estimator scales, so it goes down with the rank. So the most beautiful thing here is that it scales with the rank. So the smaller the rank will be, my estimator of the error would be very close to the true error, and it will adapt to the rank of the matrix. So the smaller the rank, the better error estimator I will have. Okay, is this clear? If it's not, you wait 5 more minutes, and because I'll define all this. But I would like to announce what we're gonna get in the next 5 minutes. And once we have that, we're gonna use it to construct the algorithm that can select which submarkets you do. All fine? All right, so this image is adaptive because it adapts to the rank, and it's honest because we can prove that with high probability, it's the true one. All right, so how does that work? Let's go back to our movie example or the music example. I have some entries, sample 1, some twice, and most of them 0, obviously. I have low budget. And I would like to construct this estimate and prove that this is error. So first, what I'm going to do, I will find these double sample entries. And I will construct kind of the data set. So X, so this is a position of the matrix, F1b is X. And this is first value, so smiling cat, or here smiling cat and frowning smiley. So I will comprise these triplets, for all the double samples. Let's say if I have 3, I just forget about them. Let's keep things simple. So I create this data set. So I will just focus on this and this. And then I empirically estimate the variance, right? I do the simplest thing possible in statistics. I'll just do the empirical estimator of the variance. So I look at how these are kind of agreeing with each other, right? So I try to see what's the variance between yi, between first smileys and the second smileys, right? And so how do the matrix, for our estimate of the matrix, how they're similar. Right, so I just do the sample variance estimator, the same that we know from high school. There is nothing simple, nothing difficult here. So this will be as good as many. I have these double entries here. And how many double entries they will happen? Of course, this depends on which model we have. So in the other model, the number of entries is 0. So this will be impossible to define. But here I have these double entries, and this is the distinction why we can construct such an estimator. And we can show, and also I can give you a reference, with a high probability in our regime, we get at least this amount of entries, so n squared over d squared. So we can actually bound the number of entries, lower bound. We can say that with high probability we have at least this amount of entries. So something that's, of course, increases with budget and decreases with the size, as we would believe. And then also we can show later that this, so the estimator itself, and this is kind of the confidence interval. So in normal statistics, you can say this is mean and this is a confidence interval. In matrix, this is the estimate of error and confidence interval. And the confidence set I defined, let's look at my matrix M hat and look at all matrices that are within this value away, in a Frobenius norm, from the true value. And I'll call these confidence regions. And then we will have that this is smaller than something scaling the rank. So the smaller the rank, I repeat this, and we'll keep repeating this. Smaller the rank, the smaller the error. Oh, so what was here? All right. So we have this adaptive uncertainty. The uncertainty of our estimators adapts to the rank. All right. So just quick idea like how this could actually work. I'll not give you the full proof, just like idea. So if we have, if the people are completely random, there is nothing we could learn. But people are not random. You are like your friends, even if you try to be unique. Then so if we sample matrix coordinate model with some completely random opinion, we get something like this. If the people have smaller complexity, then the rank 1 example is something like this. It's easy to see this is rank 1 matrix because look, this is vector. This is just a opposite of this vector. So this is flip vector. This is the same vector. This is another opposite of the vector, right? So this is rank 1. One vector is enough to describe all the matrix, right? And so this is the full matrix that we never know. Now, what happens in the model? I get samples from this. So for example, from Bernoulli model, I get only one. So no noise, so I get something like that. And so what actually matters in the completion, I can just focus on the ones that they kind of form these squares. Because from this I can kind of decide whether matrix is one rank or full rank. And I can construct some kind of examples that I will be able to show that this thing is not enough for me to decide whether I'm here. Or that means that I need a lot of examples to know whether the matrix is full rank or one rank. So this is just an idea how the proof goes. I mean, the real proof is not like that, but this is kind of like idea that we have the full matrix. We kind of look at the squares, and so this is for rank 1. For bigger rank, it's slightly more complicated. That this is the main idea that I wanted to give, because I would like to talk now about the algorithm. So what we do? Let's go back to our problem, right? We try to have these different regions that I want to decide where to sample, right? Like, let's solve something practical with it. So these are corresponding to some matrices, the real matrices that we have. We will never know. And after n samples, we can construct some of the estimates. So these will be estimates of the 3 matrices. And and how should we sample? And the answer is, well, it depends what you want to achieve. What do you actually want to minimize? What do you want to achieve with the estimation? What does it mean learning about customers, right? So you can think of, for example, maximum loss. I look at all 3 matrices and I see which one has a bigger loss. And this one is my final loss. And I want to minimize that. Or average. I would just like to average them. Or average by size. And actually this influences what your algorithm will do. So in general, we can kind of create a family of the losses that have all these cases in here. And so, you can see that if you set this to 1, you get average loss. If you set this to 0, to infinity, you get the max loss and so on. But in general, what you try to see, you look for all matrices, you compare with the true ones that you will never know. And then you sum over all matrices, and then you kind of scale it, depending on what you actually care about the most. And so what we like to show, if you want to have algorithm that have some kind of guarantees, that this is small, and this goes to 0 fast. All right. So I just parameterize this parameter by p. So by p actually decides in which cases we are. I mean, this is just example of the cases. All right. We can also have extension. We can weight it here, and for example, try to minimize the error we make per person this way. So there's only assumption that I will have here. So I'm not assuming that I know the rank. This is like the main thing of this presentation. But the only thing I assume that the entries of the matrices are bounded, and the norm is also bounded, right? So, and also the information that we get. So the rating is bounded. So I can have rating between 0 or 10, but not infinity, and the maximum entry of the matrix is bounded too, right? So I think these assumptions are reasonable, because if you, for example, one thing have a really almost infinity value, if you miss this one, of course you have a huge error, and there's nothing else you can do that. So now with the tools that I described, I present this algorithm called mallocate, like matrix allocate. So the main loop, what it does would be it picks matrix mk, We'll discuss it how, because that's the most important thing. But then it gets samples from this matrix. So that means I call somebody, gets the information. You get the estimator from it, estimate the error, then estimate the upper bound on the error, and decides if I want to keep the estimator or replace, keep the old one or get a new one, right? This doesn't even make a sense, because it's like why I should even keep the old one. Maybe the new one is better. Always, because it have more samples. We'll discuss that. And then we keep that doing it. So this is a high level. So now the low level version. Before that, of course, at the end, we output a matrices, completed. And this is, okay, we finalize our goal. Our thing is completed. These are what we think all customers like. And we will prove that error of it is low. And we will also, of course, we'll say how exactly it does. So now let's talk about all these simple procedures. So new samples, that's very simple, right? Like we don't sample one for the analysis. We also, for example, always can sample like 2, 4, 8 next time, right? To have simplified analysis. And so, for example, in this case, we just sample uniformly random a person from the market and get a new sample. Get estimator, well, we use this square root lasso estimator that was analyzed by Olga Klopp, because for that we have guarantees and we know exactly how to set this regularization parameter so it will adapt to the rank. That's what we discussed. Another thing, how do we estimate the error? Well, exactly as we said before, we look at the double entries. To be also statistically correct, we should split half of the samples and use the estimator, and use another half of estimate to estimate the error, so you don't have any statistical dependencies. That's a detail for now. And then we create this upper bound on the error, which decides what we do. So we already decided, okay, this is our error. Upper bound on the error is something, our estimator that we created with this covariance, simple covariance estimator, plus some confidence band for this. And then we look at if we improve the estimator. Okay, so again, okay, why do we need to look if the estimator is bigger, right? So we look at this value for the previous estimator for each of the matrix and for the new one. Any ideas why we could actually even preserve all estimator with smaller number of samples? The reason is that we could just get lucky at the beginning, and our estimator, even if it has no guarantees to go to be better, is almost, for example, perfect. You know, it just could happen by chance that our first estimate with one sample is perfect. We cannot guarantee this, but it could happen. But what we know with our procedure of the error, that no matter how this estimator that came, that somebody, think of it, or we get it from this procedure, we can estimate its error. Right? And it could be that, later, the nature, it always satisfies our guarantees, but later it's just worse. Because first was perfect, well, and then we get reasonable estimator with 4 samples, reasonable estimator with 8 samples, reasonable estimator with 16 samples, of course getting better. Of course, no, the previous, it's not getting better, the upper bound is going better. Upper bound on the quality of the error. So, and it's actually important for our analysis that estimators that always improve, in particular, upper bound of the estimators over improve. So to keep this upper bound going down, we will not keep estimators that's potentially worse, obviously. The upper bound is potentially worse. I hope this was clear. I can re-explain this maybe better if this was not clear. All right. So the amazing question: how do we get this estimate? How do we choose this? Okay, well, I should also say that how do we actually pick the estimate? So once we have all the estimators for the matrix, we should pick the matrix next. Well, and pick it according to, I'll go back to the slide, to the loss that we have. So if we are optimizing, for example, for max loss, well, we want to keep the max error to be minimized. So we look at which of the estimator has the biggest error, and we pick this one. right? If we have the average loss, we kind of do the same. We look at the one that has the average error, and we pick this one. All right. All right, and now we would like to see, with this procedure, what we can guarantee for this. So how good are our estimators? So for example, for this max loss, so again, max loss is I look at each of the matrix that my algorithm output and look which one has a worse loss, so which one was completed the worst. And I said, okay, this is the error of your procedure. Obviously, you should make this as small as possible. And so for this algorithm, I can prove, and we prove that the max loss of the estimator, so maximal error of the matrix, scales with a function depending on the rank. So of course it decreases of the rank without knowledge of this rank, right? So all these things was that you can adapt to all the matrices without knowledge of the ranks of the old matrices. And you can see that even the max loss, it's about one matrix, all ranks play a role in this. All ranks of all matrices play the role. And so you can also question why there is RK decay, but you can also think of it that, okay, RK decay is stuff that's coming from estimator, and then this additional D squared that is coming from the estimation procedure of the error loss. But you can just not believe me that this is a good one. Right? Maybe somebody will come and say, well, I have much better procedure, instead of, have a smaller version, right? That you can d to the power of 2 or square root of this. You can even claim that there is a better thing to do. And like I show you otherwise. But what I can tell you for this one, we already know the decreases of the rank without the knowledge of it. And again, this was only possible because we could estimate the error, and we know it's impossible to do in Bernoulli estimate, right? So this thing is kind of magical only for the cases where you have adaptive estimation of error. And I see this is not often the case. So wherever, I want to think of not just on the matrices, but wherever you can estimate your error, you automatically have this procedure that adapts to the complexity. Very simple. And so this is for max loss, and for general P, we have also something, scaling with a P. Obviously, this is a generalization of this one. If you care for other losses. I'll not go for detail there to leave some part of question, but then now you can say, is this as good as we get, as can get? Okay, so I already said this. So complexity depends on the rank on dimension, as we hope for. And if you actually look at the complexity, so one way of reading this slightly complicated thing, we can I define this complexity not just rank, but rank and the dimension. But dimension I know, so it's not that important. So if I look at the complexity of this one, I can just rewrite and all complexities as a vector of this complexity for each matrix. I can just rewrite the whole bound as the norm, P over P1 plus norm of the vector of this vector of complexities, right? So I can just read this much better. And why did I do that? Because I would like to compare it to the sampling uniformly and random. Because you can just say, why do all this complicated stuff? You could just, every time step, randomly sample matrix. Well, this is what A/B testing does, right? And so in that case, we have complexity that scales with K, so the error that scales with K times, and then the P norm. And so the simple calculation would tell you that this is always worse, or special cases when the complexities are same. It's not. It's always worse than our algorithm. And it could be much better if there are different complexities. Of course, the glory of the algorithm comes when you have disproportionate complexity between the markets. If people are coherent within markets, well, there's nothing smarter you can do in kinds of this easy problem. And another thing that you can ask is how good is this? Well, here I'm only showing you it's better than the silly algorithm. Well, maybe it's not enough. Maybe there is a smarter algorithm that can do that. And for that, we first try to run it. And so we created some matrices with rank or dimension. So we created matrices on different ranks for ring 40, and then one matrix at rank 40, and the other ones at rank 10. And then we try to do it uniform allocation. And so this is how the error decreased. And then we try to also run it with our estimator for our sum loss. So this is what we want to optimize, and also for the max loss. And also we try to also do the opposite to see that, okay, if we optimize for max loss, then max loss decreases, and we optimize for sum loss, that's here, the sum loss decreases, right? So this is for kind of a sanity check that we get what we have, right? So for sum loss, this is equal 1, so this is better, and when we optimize for max loss, it's worse than for the sum loss. But it's always better, even with the wrong objective, than the uniform allocation, which is subselecting one matrix per row. So another example, we try to do some more complicated stuff. So we have a lot of matrices with scaled rank, and we even here complain it to best possible stuff. So we compute it in advance. So this is impossible to do. We compute it in advance, like what would be the optimal allocation if some god gave us the rank of the matrix, and so this was the optimal allocation, and we observed how close to optimal this goes, right? So this is a proof by picture that our algorithm is almost as good as in an impossible hierarchy could give. But you could not trust me with this example, and we tell you, well, give me the proofs. And so we did the lower bound, and so we actually proved that it's not possible. There is no algorithm that could do better than. So again, this is what we are doing. So complexity scaled by the norm. So the rank times dimension cubed, sum. Okay, I think I also was wanting to go over proof, but I have 5 minutes. I can give it offline if somebody is interested. It's not possible to get bigger. It's not possible to get better than rank times complexity cubed. So if you look at the difference between upper bound, what our algorithms get, and minimax lower bound, the only thing that you could improve is the log k. And why this? Log dimension. And so where is this log of the dimension coming from? It's coming from the estimator itself, because it was already there. So if somebody comes with the better estimators, and for some models that already exist, then we also inherit this lower bound and we get rid of this log. Okay, so in minimax sense, this is as best as you can get. So it's minimax optimal out to these log factors. And it also, even for our lower bound also applies even for algorithms that know this rank in advance. So even if you know rank in advance, you don't do better. So that's quite surprising. All right, I just said that. Okay, I'll skip the proof of the interest of the time for the lower bound. And so I'll summarize it. So in this talk, we talk about how we can do this active adaptation to the different complexities. So again, I talked about 90% of the time about matrices, but you can talk about any substructures with different complexities and estimating error. I try to convince you adaptive inference is necessary. So it's not enough to have adaptive estimation, so the estimator itself, but you need to have adaptive inference that includes estimation and uncertainty quantification. So knowing how good is your estimator, so quantifying not only your error, but error of your estimate too. So this is necessary. I just said this thing. Then I show you one example with matrix completion where this is possible. So when we have multiple samples per entries in the matrix, because we can build variance estimate of the completion. This is possible with Querul-Lasso estimator. And then our approach just takes this estimator, and if you look at everything else, it's kind of like a black box. So if you have different problem or different estimators, you can use it to solve your problem. So specifically what we did, we solved this for a matrix completion problem when we had it's already anytime as a fixed budget. So what does it mean it's fixed budget? That I said, oh, I have n samples in advance, and I'm giving you error. But it could be any time, because at any time I can stop and I give you the guarantees. But you can also think of, okay, run. I don't want to limit you how many times, but I want to have it. I want you to provide me estimator that will be true with probability 99%. So I could convert this algorithm to the one that's run as far as needed, and then at the end produce a 99% confidence estimator. and we get some simulation for that. So next step we'll try is some for recombination data set, because this is our these were just a simple estimator when we generated matrices. All right. So as I keep saying, these results are generalizable to knowing whether this active adaptation is possible or not. And one simple thing that you can also do with matrix completion, I mean, besides finding the markers, you can also complete the pictures, right? So if I scratch some photographs, I can use some matrix completion, and for example, in the allocated time, if I care, of course, there are better deep imputing methods that they do that, but I can also do it with matrix completion, complete the matrix, just as a fun fact. And this is my talk. Thank you very much.
Any questions?
I have a short question regarding the last basically slide when you say you can apply it to images. Have you tried it actually? Or it's just
No.
AI organizers. I will tell you about multi-agent pathfinding, which is an area I've been researching for almost a decade now. I find it very exciting, and I'll tell you all about it and how to solve it. I will say, though, that you may have noticed already by the minute I've been talking that I have two problems. I'm not a native English speaker, so my accent is hard, and I'm talking very fast. So if anyone feels it's too fast for him, please raise your hand. I can slow down. I just need to be reminded. And also, I have to say that I'm very upset with all of you. The previous speaker said, please ask questions, and no one asked questions except the other speakers. Okay, so please ask questions. It'll be more fun. Okay, so can I start? Good. Okay, so this is the, who is this? Bill Gates, right, inventor of Windows and all that. This is what he says about AI. He insists AI is a threat. This is Elon Musk, founder of PayPal, SpaceX, Tesla. I'm probably forgetting some big companies, but like a big, smart guy. He insists that AI is a bigger threat to humanity than North Korea. And this is, of course, you know, right? The late Stephen Hawking, and he said that he had a paper on the threat of AI. So these are all very smart people, very techie people, and they're all very concerned about AI. So first, I want to calm you down. So this is a video from the newest version of StarCraft 2. I know you are all very serious people who don't play video games, but maybe some of you do. So this is a famous video game, and you see the agents are doing a very simple task. They only need to move from here to here. And I don't think they're doing a really good job, right? Let's say it like that. So I think before we are concerned about robots killing us, everyone, we should first solve the problem of moving agents from one place to another. And this is the problem that I've been working on. It's called multi-agent pathfinding. And the problem is very simple. It's very easy to define in a formal way. You have a graph. It doesn't have to be a grid, but this happens to be a grid in this case. And you have agents inside, and an agent, that's the AI word of saying something that moves and reacts to the world. So it can be a robot, it can be a character in a video game, it could be a drone that's flying. So the agents are located in some vertices of the graph, and the task of each agent is to move to some target location. And of course, the big problem is that we do not want the agents to collide, right? This is like the main concern. So for example, here is a possible solution. This is the motion of the agents until they reach their goal. Again, a very, very classical problem. It has many names. Multi-agent pathfinding is one of them. It's also called cooperative pathfinding, multi-robot pathfinding. And it's a really important problem in many applications, not just video games, which we've seen before, but also in automated warehouses, which is a very important application these days. This is from the Amazon warehouses. Also for air traffic management. This is, again, a multi-agent pathfinding. The agents here are the planes, and the path where there are the air tracks, and we don't want the planes to collide, right? And of course, if we look forward to the future with autonomous vehicles, then this is, of course, again, a multi-agent pathfinding problem. So it's, on the one hand, a very classical formal problem. On the other hand, it has really important timely applications. Okay, so what will I talk today? I will talk about different methods for solving the multi-agent pathfinding problem. But I admit I have a hidden agenda. And the hidden agenda is that this is the RAAI, right? The Russian summer school for AI. And it's often confused that AI is machine learning, and I want to tell you no. There is more to AI than machine learning. This is a talk about AI, but not machine learning. Okay, machine learning is important, but there are other cool stuff. So the agenda specifically, I'm going to tell you about heuristic search, which is a fundamental AI problem-solving technique, which is also used to solve this problem. Then I'm going to show you what happens when classical heuristic search problems do not work. And this happens specifically in this problem of multi-agent pathfinding. And I'm going to talk about the most common approach to solve the problem, which is called prioritized planning. And then I'm going to talk about optimal multi-agent pathfinding, how to solve this problem optimally, moving all the agents to their goal location, but as fast as possible. And I'll then talk about what happens between optimal and not optimal with approximately optimal algorithms, and what's the difference between planning and execution and robustness as long as time permits. And I'll end with open challenges, with hopes that at least some of you would be excited about this and would like to know and work on this more. Any questions so far? Good. Okay, so what is heuristic search? Maybe some of you know, but I wanted to go as broad as I can. So heuristic search is a very, very general problem-solving method. In fact, maybe you've heard about GPS. Yeah, okay, so what is the acronym for GPS? What does it stand for, GPS? General problems. So good. So it's not the satellites. Well, it is, but it is. But before the satellites, we had the general problem-solving algorithm by Newell and Simon, the forefather of AI, and that was basically a general technique for solving all problems in the world. And it was basically heuristic search. Okay. So how does it work? Heuristic search. I'm going to explain very, very briefly because some of you know and it will be boring, and other ones you don't know. It will be too much. So I'm going to try to go in the middle. So in heuristic search, we have two states. We have a start state and a goal state. And to explain it simply, I'll take a simple puzzle. Maybe you are familiar with these puzzles? Yeah, this is. Yeah, right. Rubik's cube and tile puzzle. Yeah, good. Okay. So you want to get from the original configuration of the cube to the end configuration. I'll explain in a minute how that relates to multi-agent pathfinding. And in search, you need to define a start state and a goal state, and the way you move from state to state, which are what we call operators. Okay, so in the Rubik's cube, how many operators do we have? Yeah, if you're doing like this, then my job is done. Yeah, okay, how much? No? Okay, yeah, you have six sides, and in each side you can 12. Yeah, 12 is a good answer. 18 would be also a good answer, but they're all good answers because in each side you can do two clocks. Okay, but drawing 12 would be hard for me, so I drew 3. But I hope that's okay. And how do search algorithms work? Well, what they do is they look at the start state and they expand it. And what do I mean by expand? They apply all possible operators and see which states you reach to by a single action. And that would give us, let's say, these two states, A, B, and C. And then the search algorithm, what they do is they choose some of these states to expand again. Okay, so this is the action of expand. You take a state and you apply all possible operators to it. And then the algorithms continue by expanding more and more and more and more states until hopefully eventually before the end of our life, we reach the goal state. And once we do that, then we have a solution. Okay? Okay, good. So now, but what is the problem? The problem is that the search space, the space of all possible states is very, very, very large, even for Rubik's cube. So the big question is, which state to expand? Do we expand A, maybe D, maybe E? Okay, and there are a bunch of AI techniques of how to choose which state to expand in an intelligent way. Okay, so this is not a tutorial on heuristic search, so I won't go covering all of them. So I'll just go to the bottom line. If you want to find an optimal solution, there is one algorithm that stands above the rest, and this is called the A-star algorithm. And under some certain conditions, which I will not go into now, A-star makes the optimally effective choice, meaning it chooses to expand the minimal number of states. Why is that important? Why is it important to expand a minimal number of states? Less time, right? Every expansion, that's a CPU time. It takes some CPU cycles. And so I want to expand the minimal number. So in some sense, A-star, this algorithm which I have not explained, but believe me, it exists. So it chooses to expand only the minimal number of states. Again, I'm rounding corners. There are some technical details there, but in general, it means that that's the best algorithm you could do. Again, like I myself worked on several enhancements of A-star. There are many enhancements of that, but under certain conditions, it's a good choice. Okay, so then we have a general method to solve problem. We have a heuristic search, and we have the best algorithm we can do. So now let's apply that to our problem, the multi-agent pathfinding problem. So just to remind you, here is a very, very simple multi-agent pathfinding problem. You have the red agent, it wants to reach its goal, and the blue agent, it also wants to reach its goal. And now we want to define it in terms of heuristic search. How do we define a problem in terms of heuristic search? Well, we need to define a state and a set of operators. Okay? So, and what is the start state and what is the goal state? So this is the start state. How would the goal state look like? In their goal, right. So the red is here and the blue is here. Exactly, yes, good. Okay, so this is the goal state. Okay, so now the question is, what is exactly the state in our case and what are the operators? Okay, so let's start by the simplest form of multi-agent pathfinding problem, which is the single agent pathfinding problem. Okay. So this is only one agent. What is a state in this world? It's just the location of the agent, right? And what is expanding? All single steps, right? Okay, so let's take a very simplistic view of the world and say that the agent can move only to the 4 cardinal directions. Okay, like no diagonal move, just to make it simple. Okay, so how would the state space look like? You would start with the state, up, and then you'll look at all 4 possible steps, and then you will continue. And now, if you remember, I've said that the problem in heuristic search is that the search space might be very, very large. So let's try to analyze that. In this very, very simple problem, how many states do we have? 20, right? So we have 20 states, all possible options. So it's a very easy problem. There is another thing that matters to heuristic search, which is the branching factor of the tree. That's the degree of the tree. Okay, so what is the branching factor in this case? How many? 4, right? Okay, this is an easy talk. The question are, yeah. Okay, good. So, but this is a single agent. Let's move to 2 agents. Okay, so in 2 agents, what is the state? 2 positions, like the vector of 2 positions. Good. So if I now impress you with my fancy animations, be prepared. Okay, yeah. So this is the first expansion, then the next expansion, and so on. So let's see how hard this problem is. How many states do we have? 400, like 20 to 20 squared. Good. And what is the branching factor? Okay, so that was a tricky question. Think a little bit more. What is the branching factor? How many actions each agent can take now? Yes, maximum. The maximum number of actions. There is one action that was added now, once we added a new agent. When you only have 1 agent, there is no point in waiting, right? You can always move. Okay, but if you have 2 agents now each agent has 5 options. So the number of possible actions, how much? 25. If you want to be very, very petty, you would say 24, because there's no point in both of them waiting, but I'm with you. 25, so that's 5 to the power of 2. Okay, but you can imagine that 2 agents pathfinding problem, that's not a reason to give an invited talk, right? So let's see what happens when you have k agents. How would that look like? The states would be a vector of k locations. How many states in the state space? If we have k, not 2 agents, but k agents, okay, like 20. How many states will we now have? 22 to the power of k, right, good. But that's not the hard part. The hard part is this. What is the branching factor? How many children do this start state have? 5 to the power of k, good. And that's hard. This means that multi-agent pathfinding, which in short we call just MAP, that's a very, very hard search problem, because search algorithms are very good. Like all these fancy algorithms like A*, they are very good in telling you which state to expand. But in this case, a single expansion costs you 5 to the power of k. That's too much. Right? Even if you have like 20 agents, which is not a very, very large fleet of aircraft, for example, then you're doomed. So we need some better technique. Okay? And the key idea is that we want to plan for each agent separately, because when we're planning for them together, we get this combinatorial blow-up. But we want to solve for each of them individually. But the problem is, how do we plan for each agent individually, but still make the solution sound, meaning there are no collisions, complete, meaning if there is a solution, we will find it, and optimal, meaning the solution is very, very fast and efficient. Okay, so this is the challenge, and I'm going to show you the first approach. What I like about this approach is that it's very, very, very simple, at least the basic form. It's called prioritized planning. I'm sure that if any one of you would have thought about this, or maybe written about this like 30 years ago, you would write this paper also. So what is the idea? Here is this 2-agent problem. Again, red agent to red house, blue agent to blue house. And in prioritized planning, we set a priority to the agents. Let's say the blue starts first. So we plan for the blue, ignoring completely the red one. So it will do something like this. Now we plan for the red one, but we consider the states where the blue were at. These are like obstacles, like a wall. Okay? So now if we do that, how would that look like? We'd move 1 step forward, and now what the agent would do? It would have to wait in its place and then pass. Okay? And if we had the 3rd agent, it would do the same, but the first 2 agents would be blocked. Right? So this can continue to n agents. Very, very, very simple, right? Okay, let's see how efficient this is. So what we did is if we have n agents, we run n path-finding problems, but let's see how complex they are. So if we are the first agent, that's a very simple path-finding problem. We already covered that, right? This is basically the state is single agent location, and the number of states is 20. The branching factor is 4. Very easy, right? Now let's think about what happens for the second agent. Okay? So we reserve this path of the first agent. That's blocked now for the second agent, and we want to plan for the second agent. Okay, so how would the search space look? It starts here, and then it expands, right? Okay, and what am I missing here? The fifth, exactly, yes. So now it's no longer just a single agent pathfinding problem as usual, because we need another option of staying in your location. So what is a state in this setting? It's not just the agent's location. What it is? What is each like circle represents? It's not just location. No, that you're close. It's not a decision, but it's the represent a state of the world. So and the state of the world is not just the agent's location, but it's something in addition. What? No. Time. Good. Yes. So now it's not enough to tell you the agent is in location 13. You need to know when, because it's different if he is in here at time step 0, and then it cannot go here, or time step 2 when it can without collision. Okay. So the state is now a pair of location time, and that means how many states do we have in the search space? If we totally expand everything, how many states will we have? How many? Infinity, you're right, but let's be less pessimistic and say that it's the 20, the possible location times the maximal time it takes for all agents to get to their goal. Okay. And the branching factor, how much should it be? How many children do we have in every state? How many? 5. Good, right? It's 4 plus the weight. Okay. Yeah. Okay. Good. So basically, you can think about it as the agent is searching in a 3-dimensional space. This is the spatial dimension, but it also searches in time dimension, because some of these locations are blocked in some specific time steps. Okay, does that make sense? Okay. Okay, so let's analyze this. What is the complexity of all this? Well, it's still polynomial, because the number of states in the graph times the time of time step, that's more, but that's not 5 to the power of k, right? That's not exponential. Are the solutions sound? So when we get a solution, are we guaranteed that there is no collision? Yes, right? Yes, because we avoid it. However, what about completeness and optimality? So if we have a problem, and the algorithm tells you, no, I don't find a solution, does that mean that really there is no solution? Here is the caveat of prioritized planning. No. Let me show you an example. Okay. So the red agent wants to go to here. The blue wants to go to here. Is this problem solvable? Yes, right. So the red agent would go up, and then the blue would come. However, let's try to solve it with prioritized planning. Which agent should we choose to start, blue or red? Choose one. No, let's choose blue because my animation is for blue. Okay. Okay. So blue starts its plan to go to here, and it stays here. And now, no matter what red tries to do, he's stuck. He can never get to its goal. And of course, if we chose the other way around, it still would not solve the problem. So, prioritized planning, this approach, it has many plus. This is the industry standard, I would say. Like most industrial applications use some variants of this approach, at least to the best of my knowledge. Because it's fast, it requires almost no coordination between the agents. However, it is incomplete, and I didn't talk about it, but of course, if it's not complete, the solution it gives are not necessarily optimal. You might get more efficient solutions, where the agents take fewer steps. Okay, there are many improvements, however, because this is so standard in the industry, and it works well in many cases. So there are lots of improvements: window hierarchical cooperative A*, conflict-oriented A*, reprioritization in safe intervals. This is by Konstantin Yakovlev and Anton Andreychuk, who are here. They actually are going to give a workshop on this topic in Friday. Okay, so if you want to get like hands-on experience, you can get it from the best. Okay, but I don't want it to depress you. So this algorithm works well in practice. Again, I don't know exactly what's happening in industrial applications, but as far as I know, this is from Amazon. I don't know if you've seen this video. This is the Amazon's automated warehouses. It's really impressive. I've been there in October. And you can see this is a multi-agent pathfinding problem. Right? The agents are the cute robots. And see how many are moving together in a very elegant way. So this is working. However, we want to make it work better, right? We want to have a solution. We don't want to have any case where the agent starts to work and they say, no solution, I'm stuck. We want something that is complete. So I can ask the question of, this is a theoretical question, can we get a multi-agent pathfinding algorithm, which is on the one hand complete, but on the other hand, it's efficient. And by efficient, I mean polynomial, like not something exponential. You are familiar with like NP hardness and all this kind of thing? Yeah, good. Okay, so what do you think? Can we get an algorithm that's on the one hand complete, and on the other hand, polynomial time? Guesses? No. Okay, who says no, raise your hand. Who says yes, raise your hand. Okay, yeah, okay, so to me, the solution was surprising, yes. And why? You can look at this problem actually as a puzzle, like this puzzle, for example, or Rubik's Cube, because you have the agents and you need to move them to their location. And I don't know how much have you played with this puzzle or with Rubik's Cube, but there are like procedures to solve that. First, organize the corners, then organize one plate. So there are, and these are polynomial techniques. Like I think every smart child that invests on this like several weeks, maybe also YouTubes it, then he'll get the procedure for solving Rubik's Cube. So there is a similar procedure for solving the multi-agent pathfinding. If you want to see another procedure for solving Rubik's Cube, here is another one. Okay, so I'm going to get back to, so we wanted to solve the problem. So we have a solution which is sound, which is complete. I'm not showing you the algorithm. It's complex, and it's beyond the scope of like an hour discussion. And also because me personally, I like to ask the third question, can we get to something that's optimal? And again, optimal is an important question because if it's a warehouse, it will make it spend fewer energy. If it's aircraft, fewer fuel. So that's an important task. Okay, so maybe before we talk about optimal multi-agent pathfinding, we should ask the question, what is optimal? And I'll show you two possible solutions, and then I'll ask who is better. So solution A, agent 1 walks 1 time step and gets to its goal, and solution 2, agent 2 takes 5 time steps and reaches its goal. Similarly, in solution B, both agents take 4 time steps, and I want to ask you, which solution is optimal, A or B? Okay, so when would you want a solution A? Good. When you want to optimize fuel, this spends only 6 fuel cells. Okay, when would you want option B? For time. If you want to have when all the agents will finish their goal, then solution B. So this is the technical term for these different cost functions. Is make span and sum of cost. Make span is exactly time. It's the time until all agents has reached their goal. So the make span of this solution A, for example, is 5, because only at time step 5 they're all in their goal. Sum of cost is, as it sounds, as its name suggests, it's the sum of the agent's cost. So in this case, it is 6. So just to make sure you're with me, what is the sum of cost of? Yeah. What? Oh, so because it's 1, 2, 3, 4, yeah, 4 A. But I want to ask now. So what is the sum of cost of solution B? 8. Good. And the make span? Good. Exactly. Good. Excellent. Okay. So now I'm going to save the. I won't do the poll again. I'll just tell you that finding optimal solution for multi-agent pathfinding, optimal in the sense of make span or optimal in the sense of sum of cost. These data are both NP-hard problems. Okay, but now this is AI, and in AI, unlike any other aspect of computer science, we see NP-hard and we laugh. We will solve it anyhow. And what you can see here, for example, is this is the number of agents in the x-axis, and this is the success rate, the percentage of cases we were able to solve in reasonable time, and reasonable time is a couple of minutes. And you can see that, and each line is different algorithm, no matter what are the algorithms, but you can see that the best algorithm, for example, it is able to solve problem with almost 75 agents almost all the time. Okay, so even though it's NP-hard, modern, and this is a slide, this is a figure from 5 years ago. So current algorithms are even faster. So there are algorithms today which are find optimal solutions and guaranteed. It's not just luck. They are guaranteed to find an optimal solution, and they're able to solve more than 100 agents, even though the problem is NP hard. And just to remind you, what is the branching factor of a problem with 100 agents? 5 to the 100, and you know that's a big number. Right? Okay, so there are many algorithms. Of course, too much for the remaining half an hour. All of these algorithms are optimal algorithms. I decided to choose a subset of them to tell you about them. But of course, this is very painful for me because I like all of them. But I chose only small examples. I hope this will be fun. Okay, so the first algorithm, which is called independence detection, is very simple, and it's very simple but very powerful. And what you can see here, this is Trevor Stanley. He's the inventor of the algorithm. I don't know how many of you have been already how many of your students have been in conferences, but when you're a student and you go to a conference, you want someone to pay your registration fees, right? Okay, so what you do, in a big conference, you can volunteer. You can stand and, give badges and all these things, and that gives you your registration. So this is what I did also in AAAI 2010. AAAI is the prime AI conference. So I did that, and I lucked out. The person sitting next to me giving badges was Trevor Stanley, and I asked him, okay, what are you doing for research? And he said, I'm researching multi-agent pathfinding. And I said, ooh, that's a cool problem, tell me about it. And so this is his idea, very simple. So this is the problem with 3 agents. Agent 0 wants to go from S0 to G0. Agent 1 from S1 to G1, and agent 2 from S to G2. So this is a problem with how many agents? 3. The questions are easy usually. Okay, so 3. So that's power. That's exponential in 3. That's not good. He proposed a very simple algorithm called simple independence detection, and the idea is again simple. Take each agent, solve it optimally, ignoring the other agents. So we are ignoring them. So let's see how it would look. S1 goes here, S0 goes here, S2 goes here. Now you check which of these plans conflict. Okay. So which plans here are conflicting? 1 and 0. Okay, good. So only for the conflicting plans, you now merge the agents, look at them as like one big agent, and solve them together. Maybe using some search algorithm. So now the problem is a 2-agent problem. And if you look at it, you solve this problem, this 2-agent problem, and you again check if there are conflicts. Now you look at this problem. If you solve optimally only agents 0 and 1 together, does the solution conflict with agent 2's plan? Think about it. It doesn't. No, because let's see what will happen. So they start here, right? And in order to solve, they need to go like this. By the time they are here, this guy is already here. Yeah. So the solution for agent 0 and 1 do not conflict with the solution of agent 2, so we can stop. And the cool part here is that we solve the 3-agent problem by solving a 1-agent problem and a 2-agent problem. And that's much more easier than solving a 3-agent problem. It's like 1 plus 2 is not 3. It's much less than 3. And the reason is because the number of agents is in the exponent. Okay. And this works surprisingly well. It can reduce a problem with 10 agents to problems of 2 or 3 agents, especially in very large and open maps. Okay. And you can guarantee optimality. So again, very simple, but highly effective. Okay, but this was a simple independence detection. Now, are you ready for the not simple independence detection? Okay, it's not. It's also simple. Okay, so the idea it's designed for this one. So look at this case, right? Agent 0 needs to go here, and 1 needs to go to here, and now they are planning for each of them individually. So let's say this is the plan for agent 0. This is the plan for agent 1. Bad luck, right? Because they're conflicted now, and we have to merge them and solve this 2-agent problem, which is a hassle. Okay, so what not simple independence detection says is, after detecting this, before you merge the agents, try to have the conflicting agent replan, but avoiding this path. So this is like prioritized planning, only this. However, we keep the alternative plan. It must be the same cost as the original plan. So for example, agent 1 now would look for a solution whose cost is 1, 2, 3, 4, but does not conflict with this one. 2 options, it might find it, 1, it might not find one. If it didn't find it, too bad, we need to merge. However, if it did find it, for example, in this case, there is an alternative solution, then we can stop. And again, we just did an additional single-agent search to avoid 2-agent searches. And this is a theme you will see in many algorithms for this problem. It's much better to solve many single-agent problems than one K-agent problem. Okay, questions so far?
Is it guaranteed to not generate any more conflicts
Uh,
when we plan for conflicting plans? Is it guaranteed to not generate any more conflicts with the rest?
Yeah, okay, so when I merge the two agents, then it's guaranteed that these two agents will not conflict. But it still can conflict with other agents. So what would, if we had a third agent here conflicting with this one, what would happen then? Good, we would merge and then we will have a three-agent problem. So in the worst case, we will end up with the whole K-agent problem together. So in the worst case, we will pay a little bit more. But in other cases, we save exponentially. And the thing is that it is worthwhile to try to solve several smaller than K problems in order to have the opportunity to finish at this level and not solve the entire K agent problem. Okay? Usually the most runtime would be impacted by the highest number of agents problem. Simultaneously, yes. Yeah. Yeah, okay, so there are two options, okay? When agent 1 replans, it is constrained not to conflict with agent 0's plan. Yeah, but this is the replanning, this is the try to avoid. So initially, he didn't know anything, right? So he planned this, and they conflicted. Yeah, now we're trying to resolve this conflict, and this is done by telling this agent, listen, he's going this way, so you should try to avoid it. Now, there are two options. It might be able to avoid it in the same cost, because this is also 1, 2, 3, 4. If it cannot avoid it with the same cost, it says no. And then it joins them together and solves them together with some optimal solver. Yeah, so this is an important thing to emphasize. All the algorithms I've shown so far, and I think I'm going to show, maybe at the end I'll say something else, but are what we call centralized solvers. So if you have a server and it gets the start location and go location, it tells all the agents what to do. Okay, if time permits, I will tell you a little bit more about what happens when this is not the case. But I would argue that if you are Amazon and you have a warehouse, or if you are an airport and you're managing the planes, this is a centralized case. Right? You tell all the planes where to go, you tell all the robots where to go because you own the warehouse or the airport. Okay? Still, it's important to talk also about distributed, but I don't know if I will have time. Okay? Okay, so this is a very simple, cool idea. However, it doesn't solve everything. So look at this case. Okay? In this case, if you'll see, S0 is here to here, S1 to here. These are almost independent problems, right? If you try to solve it, this would go here, this would go here, and you will have a conflict, and you're stuck. There is no way for one agent to solve without the other, so we will have to merge the agent together and solve this exponential, well, to the power of 2 problem. However, if you look at this, they're almost independent, right? They only need to agree who passes first through the bottleneck. And it's a shame to look at all possible combination of locations. They just need to agree on how to do that. And of course, this is a small problem, but I can enlarge it, right? And there are many ways for the agents to reach here. So it will be a shame to look at all possible combinations, and this is what we want to try to resolve in the next algorithms. Okay. So let's see, I have 20 minutes, so I think, okay, I will tell you very quickly about this one, and then I'll go to this algorithm, which is, no, okay, I'll skip it. Okay, so I'm going to skip an algorithm, and I'm going to talk about CBS, which is my favorite multi-agent pathfinding algorithm. I am biased, I was one of the authors. So conflict-based search, or CBS, when invented by Goody Sharon and et al., I'm there in the et al., the idea is that it tries to identify these almost independent cases. So if you look at this problem, I'm going to replace it with something a little bit more silly, but it has the same problem, okay? Which is the petty mice problem. So why petty mice? So you have two mice, and each mice wants to eat cheese. However, these are very picky mice. So mice number 1 only wants to eat cheese number 1, and mice number 2 only wants to wait each is number 2. Maybe not a perfect example, but I like the figure, so I leave it. Okay, and you can see that this is very similar to this problem because they have many ways to reach C, but they will all conflict. If we would have run a search-based algorithm like we started before with the looking at all possible location, they will have to look at m square options of reaching C before understanding that one of them needs to wait. If we run here independence detection, it would also always collide here, and they will have to plan together again m square states. In CBS, the idea is we only perform single agent searches, but we do them many times and under different constraints. So the idea is that we plan for each agent here, and we see a conflict between agent 1 and agent 2, because they are both planning to occupy location C at time 2. Is that clear? Okay, so now, if there is such conflict, it's clear that either agent 1 must avoid C at location 2, or agent 2 must avoid C at location 2. It cannot be that both of them are occupying at the same place at the same time, right? Okay, so what we do in CBS, we constrain one of the agents to replan, but avoid that location at time step 2. Again, doing a single agent planning. And then, but the question is, which agent should be constrained? Should we tell agent 1, please avoid this location at time step 2, or agent 2, please avoid this location? Depends on the but there is no priority. They are both I like both mice the same. They are both very cute and nice. Okay, so how do I choose? Actually, there is the correct answer is that we don't know. So what would we do? We would try both. We would try to replan for 1 and replan for 2, and then we see which one would have a smaller cost. Now, what happens if we replan for agent 1 and there is an additional conflict? Then we again branch according to that conflict. So this would create a tree of possible conflicts and ways to resolve them. And that tree, we're going to search it in a best first search manner, just looking at all possible options until we find a solution according to their cost. Okay, so let me better explain that. Okay, so now we're doing a different search, a search in a different space. It's in the space of possible conflicts and the way to resolve them. So before, a state was the location of the agents. Here it's different. A state here is set of individual constraints telling agent A, don't be at location C at time step 2, and a pair of solutions that are consistent with these constraints. So we start by no constraint at all. So each agent plans for itself. So agent 1, for example, can find S1, A1, CG. That's a plan like this. And agent 2 plans for itself, ignoring the other agent. Okay, so we have, so we have a solution. Is this a valid solution? No, right? They have a conflict here. So before, when we talked about search, we had a goal state, like the Rubik's Cube combination or all agents at their goal. The goal state in this search is where all paths are conflict-free. So this is obviously not a goal. Okay, so okay, let me convince you. Okay, so you see, this is okay, up, conflict. Okay, so now if we have a conflict, what do we do in CBS? We branch. We try to resolve it by having two options. In one option, we constrain agent 1, don't be at C at time step 2, and then only agent 1 here replans. So it's a single agent replan. It must avoid C at time step 2, so it gets to this one, S1, A, so it stays at A, and then does C and G. Okay? And on the other branch, we replan for agent 2. So if you think about it, how many planning processes have we done so far? Almost? 4. We plan for agent 1, plan for agent 2, plan for agent 1, and replan for agent 2. So 4 plans, but all these plans were single agent plans. Nothing exponential about them. And as you can see, we can check to see if one of them is a goal. And in this case, this is a goal, right? You can see that there is no conflict here, and this is we found. And if we search this tree according to its cost, so expanding in every iteration the node with the lowest cost, we are guaranteed to find an optimal solution. Okay, so we only do single agent searches, and we are guaranteed to find optimal solution. This is sound and complete and all the things that you would like an algorithm to be. Okay, so in this example, A star or any other search algorithm would expand m square states in order to guarantee optimality. But CBS, it would perform these 4 searches. Every search has only O of m states, because it's a single agent search. So we do 4M searches. So we get OM square for A star, but O of M for CBS. And this is 2 agents. Of course, we can get better improvements if you get to more agents. Okay, so if I was a good advertiser of an algorithm, I would stop here and tell you, this is the most amazing algorithm you've seen. It's wonderful. However, there is this option. Okay, so this case, in this case, A star would expand 8 states. It's a very small problem. It's very easy to find a solution. CBS would expand for 54. Can you see why? Okay. Look at how many paths agent 1 has to reach its goal. 1, 2, 3, 4. Yeah. So it has 4 options. And how many plans agent 2 has? Also 4. However, the optimal solution is neither of these 4 solutions. In the optimal solution, 1 agent must wait. So if we want to use CBS, we need to add constraints to make it wait. So we need to prevent all these 4 paths. So that means this option, although it's easy for A star, it has many conflicts and they are often colliding. So this would mean the CBS tree, that tree would be large, which would mean that here it will be less efficient. Okay. So it's very hard to say when A star is better, when CBS is better. But I will say that we have tried both algorithms in many settings. I will show you some experiment in the middle. But I will say that this was the vanilla CBS. There are a whole lot of improvements for CBS. There is meta-agent CBS, which after several conflicts decides to merge them together. There is a heuristics for how to choose which conflict to resolve. There is a heuristics for the search tree. There is a CBS where you imbue it with human knowledge that biases the agents to go to one direction and not other if you want them, for example, to obey traffic rules. There is the question of which low-level solver to solve, when we have the agent and they are solving, which algorithm to use. Also recently, we have developed, Konstantin and myself and the student, how to do CBS with continuous time when it's not discrete, but the time is continuous, and then like it happens with robots. There is also what to do with agents with volume, and many other improvements. So this is a whole lot of, nice family to talk about. Okay, questions so far? Okay, so I'm nearing the end of the talk. I want to tell you very briefly about the relation between multi-agent pathfinding and Boolean satisfiability. But just to see that to understand how background I need to say, how many of you, who is familiar with SAT problems? Okay, who is not familiar? Okay, interesting. Okay, no worries, it's okay. Okay, so what is Boolean satisfiability or SAT? SAT is one of the most famous problems in computer science. It's a very basic problem. You have a set of Boolean variables, and you have a formula over these Boolean variables. And the problem is, find me an assignment to the variables, true or false, such that the formula is satisfiable. Okay? So a very basic problem, a very basic problem. And one of the reasons why it's so famous is because SAT is the first NP-hard problem that has been proposed. So everyone knows that SAT, this problem of finding an assignment, this is a problem that's very hard to solve. So modern algorithms that want to be complete cannot solve this in time that is not exponential. However, because it's such a famous problem, many researchers since the 60s and even earlier have worked on doing very efficient algorithms for solving SAT. So modern SAT solvers, although the worst case complexity is exponential in the number of variables, modern SAT solvers can solve formulas with over 1 million variables. So these are very highly tuned, very effective algorithms. So a common problem solving technique in AI is take your problem and reduce the problem to a SAT problem, and then run one of the SAT solvers that are out there, and there are very good solvers out there. Okay? So the question is, can we do the same for multi-agent pathfinding? Can we cast the problem of finding a path for multiple agents as a problem of finding an assignment of variables over some formula? Okay, and the answer is that we can. And I won't go over the whole reduction, that will be a little bit boring. And also, it's not very hard. So the key thing is, what are the variables? What are these Boolean variables? And we have a variable for every triplet of agent time and location. And the variable is true if in the solution, that agent is planned to occupy that location at that time. Okay, so if we have 20 agents and the graph is 100 vertices, and the solution will take 100, it will be 20 times 100 times 100. Okay. However, as I told you, SAT solvers are very, very good. So, and the way we encode the problem, for example, is if we want to tell to the SAT solver, two agents cannot occupy the same location at the same time. How would we say that as a formula over these variables? It could be for every pair of agents I and j, and every location, and every time. VILT is true. That entails VJLT is not true for every I that's not j. And all the constraints that we are easily encoded as SAT, and we can run a SAT solver and get solutions. And in some cases, this is the best option. Not always, but in some cases. Okay, so there are many multi-pathfinding algorithms which are optimal, which guarantee optimal solutions. I showed you A star with ID. There are a bunch of other A star based solvers. I showed you the reduction to SAT very briefly. CBS. There is also an algorithm called ICTS, which is very nice. And the question is, okay, I have a problem. Which algorithm do I use? Okay, so myself and many others have tried to attack this problem empirically, and we ran experiments on many different graphs and variants. What you can see, the x-axis is the runtime, and the y-axis is the number of instances that we were able to solve. So higher is better. Okay, so and what you can see that in this problem, for example, the CBS was better to begin with, and then the ICTS was better, and then the CBS again. And in this problem, the ICTS was better. It's not clear. That's the honest answer. Okay, so when to choose which algorithm, that's an open question. And it's an open question for research to do. How to choose the best algorithm. So there are some guidelines that I can say. CBS is good when you have bottlenecks. A star is good when the state space is small. But like a clear formal theory, open question for you guys to solve, or for anyone who is interested. Okay, so what I wanted to do in the last couple of minutes is just tell you that I showed you two algorithms, or prioritized planning. The first one, which was very, very fast, but not optimal, not complete. And I showed you CBS, I star plus ID, SAT, which are optimal. There is a range in between. So you can take all the optimal algorithms, almost all of them, and you can create what is called an approximately optimal algorithm. So for example, in A star, we can just add some parameter there into the cost function. I won't go into the details. And you can make it guaranteed to return a solution whose cost is at most some factor times the optimal solution. And that can gain you a huge speed up. So for example, what you can see here, so X is the number of agents, Y is the number of instances solved under 5 minutes. And you can see the blue line is a CBS. So it's able to solve 50 agents, and then it's done in this particular map. However, if we run what is called eCBS, which is a variant of CBS that allows suboptimality of 1%, only 1%, and it's guaranteed to return a solution that's no more than 1% of the optimum, then we can solve problems with 250 agents. And remember that the problem grows harder, or more as you add more agents, it grows exponentially harder. So that's quite cool. So I would say if you want to solve a real problem, I would also introduce some suboptimality. And all the optimal algorithms I've shown you so far, they have a suboptimal variant that gives this guarantee. Okay. So this is planning. Now, I don't know if you can see, we have a robotic dog there, and the robotic dog wants to go here. So the plan is go 2 steps, then turn to the left and walk. Okay, can you imagine what will happen? I don't know if you can see the details. Yeah. Okay, so the plan was to go. The execution, so. But this is not just. I'm not going to show what happens here. It's not nice. But you can imagine, not just in joking settings, but if we're going to use algorithms to plan for autonomous vehicles, then we would not want them to only consider planning. We would also want to monitor execution and say something smart there. Because in real life, anyone who works on robots can tell you that the difference between planning and execution in real robots is huge. Okay, so and in this case, we would not want to have like this, right? This is not good. Although I will say that I have an algorithm of how to choose which one to blame for this setting, but of course we do not want only to blame. We want to solve the problem. So we can try how to react say something happened unplanned, how do we modify the plan? That's one question that's been researched. And we could also plan a priori to leave some buffer. And I wanted to say a minute of word about this. This is very simple because before we assume that this is a conflict. Agents are trying to occupy the same location at the same time. We can easily add robustness to all the algorithm I've shown by just saying this is a conflict, or maybe this is a conflict. And you can say that solution is K robust if it's robust to K delays or K unplanned actions. And there is computational questions of how to do that efficiently. There's a paper on that, so I won't go into it. Okay, so why I like to work on multi-agent pathfinding, and I do. I've been working on it for many years, and it's a lot of fun. So first of all, this is a real-world application. I've shown you warehouses and video games, and it's very, very challenging. However, it's not clear which approach to use. It's not that heuristic search is the way to go, or SAT is the way to go. There's many possible options to solve it, which makes the problem-solving part very interesting, because you can try different approaches and see who works and think about the relation between them. So this is a very interesting thing to do. However, execution is of course will be different from planning because it's a multi-agent problem. So this adds complexity. And there is so much left to do. How to exactly resolve that, how to choose which algorithm, and many, many cool applications. This is, for example, AutoStore. It's a real company, and they are not just planning moving like this, but they also need to digging the package upwards. It's a very, very cool setting. Also, so far we assume that the agents will do what I tell them. So if I tell them, agent go here, they will do that. What you can see here, this is a picture from Israel, where I'm from, of the fast road. And the fast road, the thing is that it's a toll road, but it's adaptive. I know that there are such in many, many countries, probably also in Russia. So if many agents go someplace, it costs more. So the question is, if every agent is self-interested, how do I bias them to search, to go to a path that's better? And there is some algorithm to that, but this is very like a small number. And you know, I presented them lots of stuff. I had lots of collaborators. I do want to highlight Ariel Fender, who was my supervisor, and Anu Sharon, who was sort of my student, which were my collaborators in many, many of these works. And I also want to highlight Konstantin, which is here, and I want to highlight him because he has a workshop tomorrow where you can actually play with these algorithms. And I think maybe you want to say a word or something on that.
Yeah, guys. Tomorrow we will be having a hands-on workshop on this thing. So basically, it's in the program, and you have to have your own laptop, and we'll code everything in Jupyter Notebooks in Python 3. So if you're interested, just go to the room with your laptop and stuff like this.
Okay, I'm done. Okay, thank you. Okay, yeah. Any questions? Yes. Sorry.
Question for non-stationary multi-agent systems, like when we don't have stations that will plan for all the agents. How can we modify this algorithm, or can we use